So we mentioned this at the end of the last video. Euler's theorem is what mathematicians call an existence theorem. It just tells you that there is one. It does not tell you how to find it. And so that's what this next bit is about, is once we've established that there is an Euler's path or circuit, an Euler path or circuit, then this gives us a clue how to find it. So once we know that a graph has one of these Euler circuits or Euler paths, now we got to say, well, how do we figure it out? And so one way is the trial and error method, but that gets a little bit complicated if there are a lot of vertices and edges. And so, that could get pretty complicated pretty fast. This thing called Fleury's algorithm is just a tool that is used to help save a lot of time. There's a video I found that's really helpful. It's just a great explanation. It gets a little bit beyond what we do in this class, but it gives you a really good understanding of at least why it exists and like kind of what it does. So I think it's a great resource. So that's why I shared it here. And so the way it works is this. If a graph has no odd vertices, then you start at any vertex. If the graph has two odd vertices, then you start at either one. Now remember, this ties in with Euler's theorem that says the only way that you are going to have an Euler circuit is either no odd vertices, meaning they're all even, or you have exactly two, and then you start at one and end at the other. Because if there's more than two that are odd, then it's not going to work. Or in fact, even if there's one that one odd vertex, then it's still not going to work. So the only time that you're going to have an Euler circuit or an Euler path is if you have no odd or two odd vertices. So that's kind of an important thing to observe out of this. And so if there's no odd, you can start anywhere you want and you're going to be able to find one. If there's two odd, you start at one and you got to end at the other. Now, as you go through them, you number the edges. And then make sure not to backtrack, right? So that just kind of tick them off, make sure you number them. And then at any vertex where you have a choice, you choose the one that is not a bridge for the part of the graph that has not yet been numbered. So in other words, and watching this video is what really helps click this number 3. But basically, and we'll talk about this as we do this example, basically you say, you choose one that is not a bridge. So in other words, you don't want to go in a direction that cuts off a chunk. And so you're constantly keeping an eye on the unused part of the graph. And so we'll kind of talk our way through one like this. So before we get started, we have to check these vertices. There's 1, 2, 3, 4, so that's even. 1, 2, 3, 4, that's even. 4, that's even. That's even. Even, 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 even. This one, Q, has 3, and this one has 1. So there are my 2. That has exactly 2 odd vertices. So it has one Euler path, and it's definitely not going to have an Euler circuit. So, and I've got to start, notice we have to start at one of them and end at the other when there's exactly 2. And so I've got to start at P, and the reason I know that is if I start at Q, there are, let's see, actually I don't have to start at P. I could start at either one. But at any rate, we'll back up. So it just says start at one and end at the other. And so I'm going to start at P. You could start at Q, by the way, but I'm going to start at P anyway because it'll look nicer. So I'm going to start at P. I'm going to go down here. So I'm going to go P to Q. and then I'm going to go, here I have a decision. I could go this way or this way when I leave Q. And neither place, keeping an eye on this, and again, watch this video, I think it'll help you. Neither place is a bridge to the rest of it. So you got to imagine the uncovered part of it. I need to get rid of that 1 and 3 just so that doesn't clutter things up. Delete, I'm going to get rid of my arrow. There we go. So there's P to Q. Neither one of those is a bridge as far as the rest of it is concerned. So I can go down here to R, that doesn't matter. And now I imagine the rest of this, and again, same thing. There is no bridge to the rest of it. So I'm going to go around here, down here, down here. So I don't want to lose track of that. That was R, then V, then W, then X, then S. It's the only thing I could do there. Then let's see. I'm going to go over to T. I could have gone this way or this way, and neither of those would be bridges either. From T, I only have one choice. I can go up to here, to U. Now, if I go up to Q, I'm stuck, so I can't go that way. If I go over to R, I'm okay. If I go down to S, I'm okay, because neither of those would be a bridge for the remaining part of it. So down to S, back up to R, back over to U, and finally back up to Q. And now I have made my way around this whole figure. I have an Euler path. It's not a circuit because I didn't make it all the way back to P, but I covered all of the vertices and I listed my sequence as I did it. So the real key there was in recognizing that that and that were my two odd vertices, and so I had to start at one of them. And turns out it doesn't matter. If I had started at Q, by the way, if you just picture getting rid of this first line, if I had started at Q, I had done the exact same thing, and I would have finished at P. So that's how you use Fleury's algorithm. And again, just keep in mind, as you get to a point of making a decision, you just don't want to cut yourself off. You don't want to go down a bridge that would be a bridge for the remaining part.